think now it's recording, right? It should be. Okay. All right, guys. Today we're gonna go through a little bit of Pytorch with convolutional neural network. Um, so I got this um, a scholarship from Facebook doing Pytorch via Udacity for 2 months. Now it's already, I think, the second week. I'm not sure, probably the third week. So I'm going through this convolutional neural network and the nitty-gritty of convolutional neural network. I'm trying to understand it. I already like understand about the MLP, which is the basic neural network. Now is the basically neural network specially designed for vision. So apparently the people there decided that the MLP, the basic neural network, is not good enough to basically to classify uh, images, especially if it's a rich images, if it's a real world images. It's good enough to classify, for example, an MNIST data, which is a handwritten um, digits, let's say from A to Z, or handwritten digits from 0 to 9, right? Because they are like kind of simple. But once you go to the real world, identifying like faces, trees, buildings, food, they are basically rich, right? They are very, very rich in textures, in colors, in all patterns. So uh, MLP is not good enough. So they come up with this new technique is called convolution, right? So I'm trying to understand the nitty-gritty. I kind of like been using that for quite a while, just playing around with it. So okay, here we go. Um, I'm just gonna try to read along here together and just to understand. This is probably like my second time to read this. Um, so convolutional layer. In this notebook, we visualize four filtered outputs, or aka activation maps of a convolutional layer. So there are four filtered output, right? And this is the input image. So I think it's trying to identify a car, probably, right? Um, so how do you decide it's going to be four filtered output? I think this is kind of just like based on trial and error, right? In this case, we just arbitrarily decided to have four filtered output, right? It's also called activation maps of the convolutional layer. In this example, we are defining four filters, okay, that are applied to an input image by initializing the weights of a convolutional layer, but a trained CNN will learn the values of these weights. Okay, so remember the MLP, the regular MLP, the simple one. It's basically there's a linear transformation, right? Y equals to what? Mx plus b, or Wx plus b. W is the weights, right? And then X is the input, and then the B is the bias, right? And Y is the output. So over here, apparently the weights, the W, it's a filter. In this case, there are four filter, and you will see later each of these filter will try to identify a specific patterns, right? And these filters are learned basically. So you can initialize it, the weights, right? But it says a trained CNN will learn the values of these weights. So basically, using the same principle as the simple MLP, or neural network, right? So you basically trying to identify like handwritten digits, and then you identify what is the correct label, whether if it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then you compute the error by using like a specially designed like error algorithm, for example, cross entropy. Once you compute the error, and then you can like minimize the error using optimizer. You can use stochastic gradient descent. You can use other kind of a gradient descent method, or even like a different approach, right? And then um, once you did that, um, you can sort of update the weights, right? Um, using that algorithm, that's the SGD or the GD or the adaptive learning rate, ADAM, and so on and so forth, right? So in this case, it's similar. It's just now the width, instead of just like one unit, one single unit, the widths are two-dimensional. Um, and oh, it's like A times B is a matrix basically. Is a filter. You call it a filter or kernel, right? Like 4 by 4, 3 by 3, and so on, right? And each of the filter basically trying to identify a different pattern. Over here, the image is a car, and then um, so there are four filters here, right? Convolutional image filters, like um, what blue, what's it, purple, red, and like light blue, right? And each of the filter going through the images, right? So for one filter, probably trying to identify a horizontal pattern, right? And the other filter trying to identify vertical pattern, and then the other filter trying to identify a mix between those, horizontal and vertical. And then the last filter probably trying to identify a more kind of circular pattern. Yeah, right. This is amazing. And then this is the filter images, right? Um, so I think in the API of convolution 2D, you kind of define like the size of the filter, this filter, like is it 3 by 3, 4 by 4, and then you also design, I think, the output filtered images. I'm not sure. We'll go through this. Okay. So, so import CV2. We're gonna just import a bunch of stuff here. We're taking the image from Udacity, and then we put it in a cv2.imret. CV2. What is CV2? CV2. Let's say CV2. CV2, I think, is a library for uh, images. How to read an images? Yeah, OpenCV. Okay, to read images to basically. Okay, that's what CV2 is. Okay, where are we now? So we putting it there. We put in calling the imret um, BGR image. Uh, CV2 color BGR to gray image as the float. This is to flatten, I think, to normalize the data, right? And then you want to show it. The CMap is gray, and then you show it, right? So this is what it looks like. Um, so probably you can see, let's say, gray image shape. No, it's not defined. Um, oh, I got the wrong one here. Oh, what am I doing? Um, yeah, I should. Okay, the image is 213 by 320. Okay. And then you can see, I think, the the values. Let's say this is the value on the first, I think, row. Okay. Whoa, look at this, right? All this. Okay. Okay, enough of that. And then next one is to visualize the filter. So we over here, we're defining the filter. So over here, we're already defining the filter. We initialize it, right? Um, but I think in the real convolution, these are the filter are going to be learned, right? Because these are the weights. So here is just giving an example what the filter can do, right? So we're putting the filter basically of 4 by 4, the shape. There are 4 filters, right? And these are the values of the filters. Um, sorry. So this is just one filter, yeah, which is called filter values, right? Um, you can like um, filter val. You can see the shape of the matrix, the filter. And then over here, we are just defining 4 different filters. So filter 1 is the same as filter val. Filter 2 is minus filter 1. Filter 3 is filter 1 dot transpose, right? And then filters 4 is minus filter 3. Okay. And then you put everything into an array. Um, and then over here is just print filter 1 as for an example, right? You can do yeah, and then you can visualize all 4 filter over here. Okay, so over here we visualize the filter. So filter 1 is like this. Um, if you notice, all of these filters add up to 0 when you add up all the rows. Oh, well, except this one, it's not 0, right? Yeah, yeah. So what do you think this filter will do? Like filter 1. Well, everything on the vertical, the first 2 vertical is minus 1. The first 2, sorry, column. And then the last 2 column is 1. What does that do? So if you have pixel here, it's going to be negative, the pixel, right? And then if you have pixel here, it's going to be positive, of course. If you have the same pixel, um, hmm, if you have a, this is, if you have the same pixel, the same like say 20, 20, 20, 20, over here it's going to be all negative, positive. Then it's going to emphasize the vertical pattern, even though it's the same. If it's like different already, like for example, this one is like 0 and this is 50, or like this is 1, for example. If it's 0, it's 0. If it's like zero point 0.1, and it's going to be negative, right? And if this is 1, it's 1. Okay, so it's going to emphasize the difference, right? Because remember the value of the image here it's just going to be very between 0 and 1, right? Do you remember we already flattened we normalized, we divided by 255. So if you look at the gray, let's say image, just the first row, see all the values is just a fraction, right? Between 0 and 1, right? So if you have, for example, if you have, I'm trying to think, what does this filter do? If you have, let's say, the value over here, let's say, the smaller fraction of this of 0, so let's say point one here, right? And then over here, which is basically, I think it's a black color, but over here is the white color, right? So it's gonna emphasize it even more because that number is gonna be even more negative, right? So let's say point 0.1 is gonna be minus point 0.1, right? And over here, point 0.9 times 1 is the same number. So it's gonna be um, this filter is gonna emphasize among the vertical lines. The is gonna emphasize more the edges on the vertical lines, I think, right? The same thing if this is like so big, like point 0.9, and then this is like point 0.1. Um, so this is going to be minus point 0.9, right? So it's going to be like really, really black, but minus point 0.9 is, yeah. If you normalize it, it's going to be like, yeah. So it's going to be, so this is just going to exaggerate whatever edges, vertical edges, I think this one, especially if you're on the, yeah. I think yeah. Um, on the it is yeah, this is gonna be especially if you have edges on the left. I think this is the edges on the right. This is to emphasize the horizontal lines, the one on the top. This is emphasize the horizontal line, the one at the bottom. I think. Okay, so define a convolutional layer. I'm still confused. What is the mean? Does it mean by convolution? Is it the whole like? I think it's the whole model. Like in MLP, right? The simple um, linear network or neural network is you also define the neural network, right? Okay, which is probably consists of, for example, the first layer consists of, gee, I forgot, I'm blank. The first layer consists probably before the ReLU function consists of, for example, 16 by 16 input, and you want to be, what is it? Sorry, 200 by 200 input image, and then, for example, y you want to have like say 10 layers, right? The first layer or 10 neurons, 10 output, and then you have a ReLU, and then after that the second layer, second hidden layer, you have, let's say, from 10 to, let's say, to 6, and then a ReLU again, and then after that you have from 6 to, for example, to, if it's a binary classification, then you have 2, and then the output is softmax, right? So that's you're defining the kind of the sequential layer or the forward layer or the neural network. So over here we're defining because it's a convolutional convolve at convolve. I think it means so you have a filter and then you are like from left to right. So like this. I think that's what it means by convolving. Yeah. So it's like these small images like going from left to right. You know, is like imagine you are like um, getting like a um, what do you call that image magnifier, right? And then you are looking through the image and then you're just like scanning it from left to right. I think that's called convolving, right? Okay, so okay, we're defining the convolution layer here. Okay, so the various layers that make up Any neural network are documented here. Oh, okay. Let's see. Start, so then end. Okay. Okay. Anyway, for convolutional neural network, will start defining a convolutional layer. Initialize a single convolutional. I'm so bad with this pronunciation. So that it contains all your created filters. Okay. Note that you are not training this network. You are just initializing the weights in a convolutional layer so that you can visualize what happens after a forward pass through this network. Okay, so you have init and forward. To define a neural network in Pytorch, you define the layers of a model in the function init, okay, and define the forward behavior of a network that applies those initialized layers to an input x in the input forward. In Pytorch, we convert all inputs into the tensor data type, which is similar to a list data type in Python. Okay. Below, I define the structure of a class called net that has a convolutional layer that can contain four 3 by 3 grayscale filters. Okay, because we want four inputs, right? We visualize four filtered outputs, right? So to get a four filtered output, we need four filters, right? So where are we? Okay, so convolutional layer contain four 3 by 3 grayscale filter. Why grayscale? Because the input is a grayscale. So if you remember here, where's the input? Yeah, okay. The input is this one, right? It's already being first being normalized divided by 255, and then also being um, just take the grayscale by using cv2.color bgr to gray. This one, right? So just take one channel out of it from three channel, right? Otherwise, if it's like a color, then it's gonna be a four 3 by 3 RGB filters instead of grayscale, which I think is gonna be more complicated because I think um, each of the four is just for one channel. So you need to have like three, four, 3 by 3 filters instead of just one. I think. Okay. Anyway. So we're just concentrating on here first. So we are importing the torch and then the torch neural network. So we are still using the .nn, and then we're also importing the function to SF, which is using SF. It's more convenient. Okay, so now we are here defining a neural network with single convolutional layer with four filters. Okay, so you are first is setting up the class net.nn.model, and then you have two function. One is init, and then the other one is forward. Okay, the init has two parameters, self and weight, right? And supernet comma self init dot init. Okay, initialize the weights of the convolutional layer to be the weights of the four defined filters. Okay, so you have the k height and k width is equals to the weight dot shape to and assume there are four grayscale filters. Okay, so here's the model self.conv equals to nn.conv2d. So this is the function you have to call inside the neural nn. So one I think is the I don't know what is one. Let's ask this. And n dot uh, con conv to d um, hmm, I cannot do this, huh? No. Oh, it's all messed up. Okay. I thought I can do shift up. No, I cannot do it. Um, okay, let's open and dot conv 2D. Oh, okay, so that's the input tensor, and then the weight filter of ship. Hmm. Okay. Why is the input is 1? 4 and the kernel size is the bias is false. The kernel size is is this the one I'm looking for? Um, okay, okay. Let's go here. I don't know. Let's see if I can do this. This is a weird way of um where is my kernel? Oh, my work here. Sorry. Okay. I hope it works here. Uh, yeah, I don't know why is this um okay, so assume there are 4 grayscale filters. The kernel size is um okay, height, okay, width, subconf width, 1000 and parameters equals to weight. Okay. Okay, let's do this. And n dot con 2D, right? No, it doesn't work. I have to do this first. And then and n dot. Come on, man. Where? Oh my gosh, where is it? Not this one. Here. Oh, oh, this one, this one. Import touch and then. Okay, there you go. Okay. Um, okay, this should work. Oh, this in channel. Okay. Okay, so it applies a 2D convolution over an input signal composed of several input planes. In the simplest case, you output the value of the layer with the input. Okay. Hmm. Okay. So the argument is the in channel is the number of channel in the input image. Okay, got it. And then the number of channel produced by the convolution, kernel size. Okay. And then stride and padding. Okay. Okay. Okay, I think I got it. Yeah. So in channel, output channel. Okay. So this one is one is because it's a grayscale, right? So only one input channel, and then you want to output four because remember you want to make four here, right? Um, we're defining four filter with four filtered outputs, right? So you want the output to have a four filtered output or feature maps called no, what do you call it? Activation maps. That's what they call it. I think they also call it feature maps. They call it like with different name. This is why it's like so confusing for me. Like what what the hell? There's so many like different names just for like just call it the output from the filter, right? So okay, where am I? Okay, so number of input one, right? And then just only one channel. Number of output four because you want to have four filtered output. Kernel size. Um, I don't know what is this. Like, okay, let initialize the weights. Okay, okay, I can just print it. Okay, okay. So here, okay. So actually, the weight is over here is 4 by 4, the kernel size. Okay, and with the stride is the like how many times you jump off the image, like because you're convolving, right? Over here, like this, like convolving from left to right. This small image, right, from left to right. So if the stat is one, basically you just like move 1 pixel to the left, to the left, to the left. I mean to the right, to the right. If the strat is two, that means you're jumping like 2 pixel to the right, and then the next jump 2 pixel, and then jump 2 pixel. Okay. So okay. Where am I again? Okay. So the kernel size, I think is the 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 filter. Yeah, this is the filter size, the size of the filter, which is 4 by 4 pixels. Okay, right? Am I correct? Yeah, I think so. Over here, kernel size. Yeah, kernel size. Yeah, it's the size of the convolving kernel. Yeah. Okay. Okay. Bias false, and then self convolving weight torch and dot parameters weight. I don't know what does this do. Self convolution weight. Okay, the forward. Okay, calculates the output of a convolution layer, pre and post activation. So convolve x equals to self dot conv x, convolve x, um, which is activating this guy, and then you activate it using a ReLU, and then you return both layers. Okay, so okay, and then instantiate the model and set the weights. Set weight torch dot from NumPy filters unsquish one type torch float tensor. I don't know what is this. Just and then model equals to net. Okay, what is net again? Net. What is net? Oh, okay. The class net with a weight print model. Okay, so this is not a model. Okay, got it. Yeah. Okay. Yeah. I do not know what is it. Okay, um let's ask the kernel here. All right. So this is from Kaggle, guys. The one I'm just opening up a Kaggle kernel. Yeah, is a weird way to search for meaning of the Pytorch, but it works for me. So hey, and it's free, right? Whatever works. What am I looking for? S- self-conflict. Um, hmm. What is what is the weight here? What is this one? Weight dot ship. Okay. Hmm. Does it have many meaning? Wait. No, it doesn't have any meaning at all. It's nothing. Okay. Torch and end up torch and dot parameter. What does this do? Okay. Data none requires grad true. A kind of tensor that is to be considered a model parameter. Okay. I don't know. Parameters are class, torch and subclass that have a very special property when used with class. Assigned as model attributes, they are automatically added to the list of its parameter. It will appear in assigning a tensor doesn't have much effect. This is because one might want to get something. I have no idea what is it doing. Okay, anyway. Okay, but I kind of understand how this like defining the model. Okay, can I like make this like bigger or something? No. Okay. So anyway, so we are defining the model here, right? The which is a convolutional layer model. So is a two dimensional, which is a matrix. Um, this is the major difference within this convolutional model with the uh, the simple model neural network, which is just like a one-dimensional, which is just a factor. So the input of this model has to be a matrices, right? Which is x times y, right? It has to be like 4 by 4 or 4 by 5 or 5 by 4. It cannot be just a um, one dimensional tensor, right? Because this is 2D, it's more complex. It's a matrix. So, and the input is just one input, one input channel, because it's a grayscale. You want to have an output of 4 filtered because you are trying to uh, kind of like trying to identify what are the 4 different patterns that you can like classify or identify from these images from this one grayscale, and you are using a filter of size 4 by 4 to 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 have that four different output, right? Feature output or activation maps, and you are just hopping one pixel at a time. That's what stride one. I don't know what stride 1, 1. Or you can ask again. Okay, okay, we'll go back here. Okay, uh, okay, stride. Because what is stride 1, 1? I don't know what's stride. Probably I can put stride, right? And okay, what's the, is it inside the, oh, okay. Yeah, I don't know why it's like that. Like, um, because over here it's just like one integer. Um, oh, probably it's the x and y. I think. I think that's the x and y. Yeah, I think so. It doesn't. I couldn't find anything here. Sorry. I think it's the x and y. See, this one like 2 comma 1, 2 comma 1. So this is probably like you're hopping on the horizontal 2 pixels at a time, and then when you go vertically, you're just hopping 1 pixel. So you're just going down 1 pixel. So, but if this is 2, then you're also going like 2 pixels down, right? But if it's like 1, just like hopping down. So this is the horizontal. I think this is the horizontal. This is the vertical hopping. I think. Otherwise, it doesn't make sense. Okay. Okay. I think I got this. Okay. So visualize the output of each filter. So you want to now visualize the output of this filter from this output after you convolve um, and with the filters of 4 by 4, and then you have four filtered outputs, right? You have this, you have this guy here, right? Um, filtered images, right? So you want to visualize that. Okay. Okay. So you're using this function. Um, so okay. Visual layer and filters is 4. Okay. And then where do you define the filter again? Um, oh, it is on filter 1, filter 2, filter 3, filter 4. Oh, it's in the filters already. Got it. Okay. So if I can just do this basically filters, and then I can just do 0. Yeah, that's the first filter, and then I can do like 1. That's the second filter, right? And then I can do 2. This is the third filter, and then I can do 3 because they're in array. Okay, got it. And then if 4, it goes back to filter 1 again. Error. Index 4 out of bounds. Okay. Anyway. Okay. Um. Okay. Um. Got it. So you are plot figure, figure size 20 by 20, and filter in range 4. Subplot on sticky text output. Okay, let's take a look at this. We'll define a helper function, visual layer, that takes in a specific layer and number of filters and displays the output of that layer once an image has been passed through. Okay. Look at the output of a convolutional layer before and after a ReLU activation function is applied. Okay, so okay, because this one is using ReLU, the convolutional layer, and and where? Okay, so what are we doing here? So we are plotting the original image. We are visualizing our fall filter, right? And then we are convert the image into an input tensor. And then you want to get the convolutional layer. And then you visualizing the output of the convolutional layer. Pre and post activation. Okay, let's open this. Okay, so if you can see, this is the filter one. This is the output. As you can see, if compared to the filter 3 and filter 4, is more emphasizing on the vertical edges, right? Of course, there's some horizontal edges also, but if you like compare it, right? Over here, it's more on the left, kind of, and more emphasized. This one is more on the right, I think, kind of, right? All right. Over here is like very emphasized. Over here is like one on the top. This one is more on the bottom, horizontal, kind of, right? Yeah, so it can like slightly different kind of pattern can identify. So this one is a pre or post activation. Oh, wait. Oh, this is before. Okay. Actually, if it's you can just use the activated layer here. The model gray image sensor, activate sensor. Let's look at the. Oh yeah, so you have two returns here, convolution X and activated X. Got it. Okay. Okay, so ReLU is basically this is the function of ReLU. Basically, the X gonna be sorry, the Y, the output is gonna be all zeros if X is like less than zero, and it's gonna be the output is gonna be whatever um, whatever X is, basically. Um, if X is greater than zero or equals zero. Okay, and this is a nonlinear, right? So, okay, we choose ReLU function to do this. And this function simply turns all negative pixel in zeros black. We see the equation picture below for the input. Okay, and then now we activate. Okay, a thing should be less pronounced, the edges, because you are clipping the negative, right? You're clipping the negative. Everything is going to be like zero again. Yeah. Yeah, and I don't know how do you like how do you hmm, yeah you can look here for example let's say conf layer, let's say ship, can you do ship? Okay, so that's a ship 1 4 210 okay, can I just get let's say just can I do that or no? Okay, so because you can see here there are many negative. Yeah, how does pixel, yeah, this is the thing I don't understand. Like negative. So it makes it like gray. Okay. So if you compare that with the activated layer, then there's all zeros, right? all the one and negative is just all zeros. Yeah, so that's why it's just all black. This one. Well, the one over here is gray. Okay, so I guess it's displaying gray then, negative. Okay, so that's how you define um, convolutional layer on Pytorch or the fundamentals of convolutional neural network. Okay, thanks for listening. I'll see you next time. Ciao. Okay, where is it?